Hello everyone, the paper I'm going to present today is multimodal sentiment analysis based on modal focusing model. I will introduce from 5 aspects: introduction, related work, methodology, experiments, and conclusion. Multimodal sentiment analysis is a research field that has attracted much attention at present. It aims to understand people's sentiments by using information from various sources such as language, facial expressions, actions, and speech. The development of the Internet and mobile applications enables people to easily access high-quality video data on platforms such as TikTok and Bilibili. Compared to text descriptions or images, video has become the mainstream media form due to their efficient way of carrying information. Generally, video includes textual, visual, and auditory data, and these 3 modalities complete each other to more accurately reflect the sentiments of the speakers in the video. In the research of multimodal sentiment analysis, research usually holds on 2 views on dealing with the interaction between modalities. One view is that the contribution of each modality to the sentiment analysis task is equal, so a simple average strategy is used to integrate the information of each modality. Another view is that in the task of sentiment analysis, the contribution of text modality is the most significant. So in the entire fusion of multimodal information, text modality is often the core. However, in certain sentiment analysis samples, there exists an imbalance of information across different modalities. The right figure shows an example of multimodal information imbalance. Faced with such a situation, the 2 kinds of interaction views mentioned above will ignore the differences between different modal sentimental information or omit the important information provided by non-textual modalities, thus limiting the performance of the sentiment analysis model. To mitigate the effects of imbalanced multimodal data on sentiment analysis tasks and effectively capture the contribution of each modality, it is crucial to give each input modality a proper primary privileges. Therefore, we propose a modal focusing model for multimodal sentiment analysis. We design a short mask model to learn the relationship between primary and secondary modality features. In the cross-modal attention model, we ensure that the secondary modality obtains short features related to the primary modality by using the short mask, and finally gets the fusion vector guided by the primary modality. We use the weighted attention mechanism to weight the 3 fusion vectors to weaken the influence of the secondary modality guided vector and highlight the future information of the primary modality guided vector. Next, I will introduce how to obtain a short mask. We use the sequence-to-sequence model with the attention mechanism as the cross-modal prediction model. As shown in the right figure, the short mask model uses sequence-to-sequence model to predict the future sequences of secondary modality from the future sequences of primary modality. By training the sequence-to-sequence cross-modal prediction model, the attention graph between the primary and secondary modalities can be generated, and the corresponding calculation precision can be performed to obtain short masks. The specific steps are as follows. Establish the attention graph. A and B respectively represent the future nodes of the primary and secondary modalities, and the depth of the edge indicates the size of the attention weight. For each row of the attention graph, we sort the attention weights, then return only the edges with larger weights between each secondary modality future node and the primary modality node, while removing other edges. Map the proceed attention graph to the short mask. The specific steps are shown below. To effectively capture multimodal information, we propose the concept of modal focusing, which customizes the final multimodal fusion vector by specifically concentrating on individual modalities. This concept is divided into two parts. The first part involves using a cross-modal attention mechanism with a short mask to fuse information centered on each modality. In cross-modal attention, we study how to use one modality as the dominant modality to interact with other secondary modalities to generate a new vector representation. Our research covers text, audio, and vision, and each modality is focused. By using the short mask to obtain short features of the secondary modalities guided by the primary modality, we generate three multimodal fusion vectors. The second part involves using a weighted attention mechanism to assign weights to the contributions of the three modality-centered fusion vectors in the final sentiment analysis task. By learning the three multimodal fusion vectors, we not only obtain the corresponding weights of each fusion vector to quantify its contribution in sentiment analysis task, but also maximize the information and future values content in the three multimodal fusion vectors to address the imbalance of multimodal information. To evaluate our approach, we carried out experiments on two well-known multimodal public datasets, MOSI and MOSEI. The basic training, validation, and testing set data are shown in table. To assess how well our proposed model performance, we use four evaluation metrics: ACC2, F1, MAE, and CORR. We test the proposed model on two multimodal sentiment analysis datasets to confirm its superiority, using the mentioned quantity metrics. In this paper, TFN, LMF, MUIT, and RMSA are selected as the multimodal sentiment analysis methods of non-modality-centered fusion for comparison, and ICCN, TCSP, MAG, BERT, and BBFN are selected as the multimodal sentiment analysis methods of modality-centered fusion for comparison. The experimental results are present in the table, where we can see that MFM achieves state-of-the-art results on the classification metrics ACC2 and F1 for the MOSI dataset, demonstrating its strong generalization capability. In terms of regression metrics, it outperforms non-modality-centered fusion methods and shows a slight lower MAE compared to MAG BERT from modality-centered fusion methods, while exhibiting superior correlation performance. To prove the effectiveness of each model of MFM, we conduct ablation experiments on MFM model using the MOSE dataset. The experimental results are shown in table. Our evaluation shows that although text-dominated cross-modal interactions outperform visual or audio interactions, focusing slowly on text reduces performance compared to the MFM model, highlighting the significant contributions of vision and audio modalities in imbalanced contexts and the necessity of considering all modalities in sentiment analysis. Removing the short mask model decreases model performance, demonstrating its importance in sentiment analysis by enabling the secondary modality to focus on features relevant to the primary modality and enhancing model robustness. Eliminating the weighted attention model results in decreased performance for the MFM model. This mechanism adjusts the importance of the three multimodal fusion vectors, boosting the contribution of useful modalities while minimizing the influence of secondary ones. Model analysis. We test the impact of different members of short features on sentimental analysis models. Evaluate using the MOSEI dataset. The results in figure shows that selecting 5 short features yields the best performance in ACC2 and F1 metrics. This is likely because when the number of short features is too low, the model fails to capture sufficient sentimental information, leading to decreased accuracy and comprehensiveness. Conversely, selecting too many short features causes the model to overly focus, weakening the masking effect and increasing computational complexity, thus affecting efficiency. In this paper, we conduct a multimodal sentiment analysis framework focusing on each modality, aiming to deeply learn multimodal sentiment information with text, vision, and audio as the core. Compared to previous studies, our approach averts the inadequacies in optimizing non-textual and multimodal representations caused by text modality dominance, as well as the potential weakening of important modal information due to simple arranged strategies. In the future, we will explore how sentimental information across modalities correlates and refine contribution handling strategies to enhance our multimodal sentiment analysis framework. Thank you for listening.